Bismillahirrahmanirrahim. So next we are actually discussing the transformation of uh, plane stress. Plane stress, as we discussed, that if two faces of this cube is free of loading, there is no loading along z direction. Only the loading is along x-axis and y-axis. Z-axis is free of loading. So that is the case of two-dimensional stresses. Or this is the problem of plane stress. If you look at this cube in this direction, you will see only a square, and you could see all these stress values on this stress element. We call this a stress element. This is a stress element in 3D form. This is a stress element in 2D state. We call it stress element, stress state at point O. And you could see that these are the stress values, but these are the stress values in XY coordinate frame. So what would be the new stress value if we rotate the coordinate frame by some angle theta? So what would be the new value of the stress component in this new coordinate frame? So for that we have this transformation of stresses topic, that how to transform the stress values into new values into a new coordinate frame or orientation frame. So if in one frame we know the stress values, for example here, let's say if in xy plane or xy frame, if we know the stress values, we know sigma x, sigma y, and tau xy, then if we rotate this coordinate frame by some angle, and our new coordinate frame is x prime, y prime, which is at an angle of theta to our previous frame, then what would be our new stress component values? So for that, we would be using the stress transformation technique. So the stress transformation technique is actually used to calculate or compute those values. And these are the equations or analytical models by which we would be doing that. So if you know the stress values in XY coordinate frame, so if the new frame is at an angle theta, then what would be sigma x prime? What would be sigma y prime? What would be tau x prime y prime? In terms of what? In terms of the known values of stresses and known value of the angle to which the frame has been rotated. So the topic is that how we got these equations, how to prove these equations, from where we got this equation, from where we got this stress transformation equation in case of plane stress problems. These are the stress transformation equations for the plane stress problems. So in order to develop those analytical models, or in order to prove the stress transformation equations, those three equations, assume the stress element, 2D stress element, as we are discussing on the previous slide, and uh, we are truncating this stress element. Let's say I'm cutting this stress element here, and this angle is theta. So we are considering only this portion of the stress element. So this is the truncated portion of the stress element. Let's say after truncation, this slanted side, the area of this slanted side is delta A, and the stress normal to this truncated side is sigma normal or sigma x prime, and this is the shear stress which is along this surface or along this area. And in 3D shape, this would be a wedge. It would be not a rectangle, it would be a wedge. This would be the stress element in 3D shape. So you could see that we have sigma x which is acting on this area, delta A cos theta. Delta A is the area of this slanted side. So the area of this vertical side would be the projection. It would be a projection. It will be projection of the slanted area. This is theta. So the projection of this slanted area or this vertical area would be delta A cos theta. And this horizontal area, which is the vertical projection of this area, and it would be delta A sin theta. So the force on this vertical surface would be delta sigma x delta A cos theta, and the shear force would be shear stress tau xy times area delta A cos theta. Similarly, the vertical force would be in terms of stress sigma y, so sigma y delta A sin theta. And this horizontal force would be shear stress tau xy delta A sin theta. Because we know that stress is load per unit area. So in order to find load, which is because of that stress, or stress which is because of that load, it is load is equal to stress times area. So and the angle through which the new coordinate frame is rotated. Now you could see that our new coordinate frame is x prime, y prime, and this is the normal, and the normal of this area is along x prime, and this normal stress here it is sigma x prime, and the force is sigma x prime delta A. Delta A is the area of this face. And the shear stress, which is along this area, it is tau x prime y prime. And the force would be, you have to multiply with the area for which this is acting. So it is tau x prime y prime delta A. So we are trying to find out the mathematical equations or mathematical models for sigma x prime, tau x prime y prime, and for sigma y prime in terms of what? In terms of known components of stress, sigma x, sigma y, and tau xy, etc. And angle theta. So what we have to do, this is the our wedge stress element, and if we look to the wedge shape, wedge stress element in this direction from the front, so it would be a right angle triangle. So from the front you would see a right angle triangle, and you could see all these stress components or force components here. And actually, in order to develop those equations, we would be resolving all these forces into its rectangular components, along x prime and y prime. Because our new coordinate frame is x prime and y prime, and we are trying to find out the stress values in our new coordinate frame. So actually, we have to resolve all these forces which are acting here into its rectangular components. In order to resolve those into its rectangular components, so the easy way is first draw the coordinate frame at these forces. So I'm drawing a coordinate frame at these forces. So this is the coordinate frame. We could draw this coordinate frame at any other point, at anywhere on the stress element. Here I'm drawing the coordinate frame. So this is our x prime, this is y prime. So next we have to resolve these forces into its rectangular components. You could see that this line is parallel here to this line, and this line is parallel to this line. This angle is theta, so this angle is theta. Similarly, this angle is theta, so this is a vertical line, and this is the alternate angle. So this is also angle. This angle is theta. This angle is theta. This angle, this complete angle is what? This complete angle is 90 degrees. This is theta, so this is 90 minus theta. This is 90 minus theta. This angle is 90 and this is 90 minus theta. So 90 minus theta, this angle will be theta. So this angle is theta. So first resolve these into rectangular components. So we are trying to resolve these into rectangular components. So first look at this node. I'm trying to resolve this into its rectangular component. So this is theta. So a component along this line would be a cos component. So this is what? This is sigma y delta A sine theta, and this would be the cos component. So here you have to write also cos theta. Similarly, this would be the sine component. This is the cos component. This would be the sine component. So this would be what? This would be sigma y delta A sine theta, again sine theta. So we have resolved this force into its rectangular components. And you have to write here this sigma y delta A sine theta sine theta. Similarly, we have to resolve this force into its rectangular components. So let's try to resolve this into its rectangular components. So this angle is theta, this angle is theta. So its component along this line would be cos component. So it would be tau xy delta A sine theta cos theta. And its other component, the other component would be along this line, and this would be the sine component. So it would be tau xy delta A sine theta sine theta. Remember that this is our coordinate frame. X prime is positive in this direction. Y prime is positive in this direction. So here you see that this component of this force is in the negative y direction. So you have to take this negative. Similarly, here these two components of these two forces is in the negative. X prime would be positive in this direction. So these would be negative when you are summing all of the components along x prime or y prime, and these two you have to take negative. Here you could see that this component is along the positive y prime, so you have to take this positive. Let's clear our drawing. So we have resolved these two forces into its rectangular components along x prime and y prime. Next, we have to resolve these two forces into its rectangular components along x prime and y prime. And for that, we have to redraw those axes, x prime and y prime. This is the x prime and this is the y prime. Positive x prime, positive y prime. And next, we have to resolve these into its rectangular components. First, let's say resolve the normal force into its rectangular components. This angle is theta. If you look here, if I extend this line, this angle is theta. So this is the alternate angle, it's also theta. So one of its component would be along this direction, whereas the other, if we resolve this into rectangular components, the other component would be in this direction. This is the positive y, this component would be positive. This is the negative x, this x prime, this would be the negative component. the theta is along this component, this would be the cos component. So delta sigma x, delta A cos theta and cos theta. And this would be the sine component. So sigma x, delta A cos theta, sine theta. And similarly, if we resolve the shear into its rectangular components, this angle is theta, this is 90 minus theta, this is 90, so this angle is theta. So into its rectangular components, one component is along x prime axis, it would be negative, and the other component would be along y prime, and it is also negative here in this case. And the theta is along this component, so this would be the cos component. This would be the cos component. So tau xy delta A cos theta, cos theta. And this is the sine component. Tau xy delta A cos theta, sine theta. So now we have resolved all of the forces into its rectangular components, along x prime and y prime. Next is what? Next is we have to add all of these forces along x prime axis and y prime axis. Okay. The stress element is in equilibrium. This stress element is in equilibrium because the stress element represents the stress values at a point. The point which represents the particle inside the material. When the material is loaded, those particles are not rotating. They are in equilibrium. They are in static. So we could apply the condition of equilibrium and condition of statics on the particle, on this point Q, on this stress element. So the stress element must be in equilibrium. If the stress element is in equilibrium, each segment would be in equilibrium. So this segment must be in equilibrium. Whatever is the coordinate frame, it must be in equilibrium. So the summation, so we are using the first condition of equilibrium. So the summation of all of the forces along x prime must be equal to 0. Similarly, the summation of all of the forces along y prime must be equal to 0. So we have already resolved all the forces into its rectangular components. If you look here, this force is along x prime and it is along positive x prime. So this would be positive. And the cos component of the this normal component, it is negative. So we have already resolved this. So just write this. And similarly, the cos component of the tau xy, which is along x prime dash, so we would get this equation. So you have to sum up all of the rectangular components, all of the forces along x prime, so we would get this equation. Similarly, if we sum up all of the forces along the y prime axis, so we would get our second equation. So if we look at our first equation, we could see our other previous value sigma x, tau x, y, sigma y, tau xy. These are, let's say, the stress values in the known coordinate field. And theta is the angle by which we have rotated, or we know that the new frame is at this angle to our previous coordinate. So somehow theta is also known. So if you look here, the only unknown in this equation is sigma x prime. So bringing this sigma x prime on the other side of the equation, and also you could see that there is delta A with each and every quantity within the equation. So we could divide the equation 2 out by delta A in order to eliminate delta A. And then bringing sigma x prime on the other side and then simplifying the equation, we would get our first equation. You have to do those simplifications at your home or in hostel. So simplifying that, sigma x prime, you would get an equation in terms of sigma x, sigma y, tau xy, and theta. Similarly, if you look at this equation, each and every quantity has delta A, so divide the equation throughout by delta A. So delta A would be eliminated. And if you look here, here we have tau x prime y prime. So, and it is positive. So bring all the other quantities on the other side of the equation and then simplify the equation. And after simplification, simplifying the equation using the terminology of using the trigonometric equations, then tau x prime y prime would be equal to minus sigma x minus sigma y by 2 sine 2 theta plus tau x y cos 2 theta. How we got this equation and this equation? From these two equations, I would give you this in assignment. It is very easy. It is just a trigonometric problem, so it would be given to you in assignment. So conclusion, after summing, after playing with these equations, you will get an equation for sigma x prime in terms of sigma x, sigma y, tau x, y, and theta. And after playing with this equation and after simplification, you will get an equation for tau x prime y prime in terms of the given stress value. How we would get this equation, that is equation for sigma y prime. For that, we have to consider the other wedge. You have to truncate the stress element, the square stress element along this line. And we have to consider this portion of the stress element. And again, we have to use the same procedure. And when you would use the same procedure, which we have already discussed for the this segment of the stress element, if you are using the same procedure, that is, you have to resolve this, you have to resolve this force, all these forces along x prime and y prime, and then you have to apply the condition of equilibrium. Afterward, you would get an equation for this sigma y prime and the same equation tau x prime y prime. So you have to also do this practice by yourself. You have to consider this portion of the stress element, and you have to draw the stress element like this, and then you have to resolve all of the forces along x prime and y prime, and then you have to take the summation of all of the forces along x prime is equal to 0, and the summation of all of the forces along y prime is equal to 0, and then you have to simplify the equations. You will get this equation and this equation. So finally, now we have the mathematical models for the stress values in the new coordinate frame. And the new coordinate frame is x prime, y prime. And in this new coordinate frame, which is at an angle of theta, you could use these analytical models to find out the stress values in any other coordinate frame. Theta could be anything. Theta could range from 0 degree to 360 degree. So if you rotate the coordinate frame to an angle from 0 to 360 degrees, then you could find out the stress, these three stress values in the new coordinate frame with these mathematical models. So we got the stress transformation equations. These are known as the stress transformation equations. So stress transformation equation for stress along x prime axis, stress along y prime axis, and the shear stress x prime y prime. So we have these three equations. Next, we want to modify these equations into some new form, which would be very easy for us, so that in order to understand the transformation of stresses. So we have these three equations. If you look here, that we have sigma x plus sigma y by 2, and this could be simplified as average stress. So sigma average is equal to sigma x plus sigma y by 2. And let's say R, you would see that why we are calling this R. R is equal to under the root sigma x minus sigma y by 2 whole square plus tau xy 2 whole square. So you could see this term here. So now what we are doing, as this quantity here, sigma x plus sigma y by 2, we are putting this average, sigma average. It is sigma average, you will see in the coming slide. So sigma average. And I am bringing this quantity, sigma average, on the other side of the equation. So we would have sigma x prime minus this quantity. On the other side, it would become minus, so minus sigma average. And you have to rewrite these quantities as it is. So it is sigma x minus sigma y by 2 cos 2 theta plus tau xy sine 2 theta. We got equation 4. Now what we have to do next, we are squaring this equation. So we have to square this equation on both sides. So squaring on this side would become sigma x prime minus sigma average whole square. And squaring, this is a plus b, so the square of a plus b. So a square plus b square plus 2ab. So the square of this plus the square of this and plus 2 multiply by this and this. So we would get that. And we are also squaring equation number 3. Squaring equation 3 on both sides. So it would become tau x prime y prime whole square. And again, if you look here, it is a minus b. And the square of a minus b is a square plus b square minus 2ab. So squaring equation 4 and squaring equation 3 and then adding these two equations. And then we have to add these two equations. After doing that, what we would get? We would get sigma x prime minus sigma average whole square plus tau x prime y prime whole square is equal to sigma x minus y by 2 whole square plus 2xy square. And the remaining things would cancel because one would be plus and one would be minus. One would be minus, so they would cancel out. So we would get this equation. Further, to this quantity, here you see this quantity. This quantity, we are saying that, let's say it is r square. So it is r square. So r is what? R is under root of this quantity. So here I have written that r is the under root of this quantity. Why we are bringing these sets of equations into this new format? That is for a particular reason, and that particular reason is that we are trying to deduce these analytical models into a graphical model. Now come and see. If you look at these equations, you will see the similarity within this equation. This equation is actually the equation of a circle. Equation of a circle in xy frame, in xy coordinate. This is the equation of a circle in xy coordinate. X minus h whole square plus y minus k whole square is equal to r square, where r is the radius of the circle and h and k is the center of the circle in that xy plane. Now compare our new equations with this equation of circle. Instead of x, we have sigma. Instead of y, we have tau. Instead of h, we have sigma average. Instead of k, we have nothing here, that is 0 here. Huh? And instead of small r, we have capital R. So meaning that this is an equation of circle in which plane? Sigma and tau plane. This is the equation of circle in xy plane. This is the equation of circle in sigma and tau plane. Here we have sigma, here we have tau. So in sigma and tau parameter, this is the equation of a circle, where sigma average is sigma x plus sigma y by 2, and r is under the root sigma x minus sigma y by 2 plus tau xy whole square. So what we have done in analytical mathematical equation, we have reduced that equation into an equation of a circle, meaning that now we are in the position to even plot this equation, and the plot of that equation would be a circle. So we have reduced an analytical mathematical equation into a graphical format. So we could plot that equation, and the plot of that equation, this equation, would be a circle, and its center would be where? The center would be sigma average comma 0. So, and axis, along x-axis we have sigma x prime axis, along y-axis we have sigma, we have tau x prime y prime. This is the tau axis, and this is the sigma axis. This is the positive sigma axis, this is the negative sigma axis. This is the positive shear stress axis, this is the negative tau axis. The center is sigma average and 0. So the center of the circle would be here. The sigma coordinate is sigma average, and the tau coordinate for the center is 0. The center would be here. It would be somewhere here. And next we need radius for the circle. So radius of the circle is in terms of sigma x, sigma y, and tau xy, which would be known to us. So r. So by having this center and then radius r, we would have this circle. So we could plot this equation into a graphical form. This is the graphical form of that mathematical equation. This is the stress transformation equation. This stress transformation equation represents what? It represents infinite solutions. The stress transformation equation represents infinite solutions. Theta could be anything. Theta could have infinite values. So we could find infinite solutions with these equations. Similarly, the equation of a circle, which we have deduced from the other equations, it represents infinite solutions for our circle. And those all infinite solutions lie on the periphery or the circumference of this circle. All those solutions actually lies on the periphery of this circle. If you look here, you could see very important points here. For example, this point, if you look here, this point represents the stress value for maximum normal stress. Here at this point A, the normal stress is maximum. Here at this point B, the normal stress is minimum. Sigma maximum is at point A. Sigma minimum is at point B. And similarly, the maximum shear stress is at point C. The minimum shear stress is at point E. This point M represents tau x prime, it represents sigma x prime and tau x prime y prime, meaning that the coordinate of point M are sigma x prime, tau x prime, y prime, and this line actually represents the x prime. This line represents the x prime axis. This line represents the x prime axis, and this line represents the y prime axis. This would be more clear when we would be discussing the Mohr circle diagrams. Mohr circle diagram is the graphical method by which we solve the problems of stress transformation. So this is x prime, this is x prime axis, this is y prime axis, and if you look here, what are the coordinates of this point? The coordinates of this point is sigma maximum, comma, and what is the value along tau axis? 0. So the coordinate of this point is sigma maximum, comma 0. The shear stress at this point is 0. So it means that this is one of the principal stress. Similarly here, if you look here, the shear stress is 0. At this point, the shear stress is 0. So this is our second principal stress. So maximum principal stress, minimum principal stress. All other values at all other points, the shear stress exists. All other points except point A and point B, shear stress values exist. It means that all these points represent those axes or those coordinate frames where shear stress is not zero. Only these 2 points represents what? These 2 points represent the principal stresses. These 2 points represent the principal planes. So one of the principal plane is passing through this point. So this is one of the principal axis. And that principal axis is making an angle, this angle. And here we donate this angle by 2 theta p. P stands for principal axis or principal plane. So 2 theta is the angle which x prime is making with what? It is making with one of the principal planes, or the principal plane is actually making with the x prime. So principal stresses occur on principal planes of stresses with zero shearing stresses, which we have already discussed. And what would be the mathematical equations? So very easily we could write these equations from here. Sigma maximum up to here, from here to here we have sigma average, and from here to here this is r. This is the radius of the circle. CA is equal to radius of the circle. So sigma maximum is equal to average stress plus r, this r. So we would get sigma maximum. Sigma minimum is what? This is sigma minimum. So this average from O to C minus CB. CB is the radius of the circle. So minus the radius of the circle. So with the plus sign, we would have sigma maximum, equation for sigma maximum, and with the negative sign, we would have the analytical model for sigma minimum. And in this right angle triangle, where this angle is 2 theta p, and this vertical is tau x prime y prime, and the horizontal, base, this is x prime. It is sigma x minus sigma y. This is sigma x minus sigma y. In this right angle triangle, tangent 2 theta p is equal to tau xy divided by this is the radius, so we have to divide this by 2. So sigma x minus sigma y by 2, and that 2 is written here. So this is the analytical model by which you could find out the orientation of the principal planes. And these are the mathematical equations by which you could find out the maximum and minimum normal stresses or the principal stresses. And here you could see that the stress element is drawn showing the principal stresses, sigma x and sigma y. It would be more clear, this concept would be more clear when we would be talking about the Mohr circle. But remember that we have developed these equations and you would be using these equations, stress transformation equations, and you would be use this analytical model to find out the principal stresses and the orientation of the principal planes or principal stresses. Okay, next, maximum shear stress occurs for. So as we discussed that if you look at this diagram at point D, the shear stress is maximum. Shear stress is maximum. So tau maximum is equal to what? Tau maximum is this distance, CD. And CD is what? CD is the radius of this circle. So tau maximum is equal to R. And R is under the root sigma x minus sigma y by 2 whole square plus tau x y square. And the angle, this is the x prime axis. And this angle is 2 theta s. This angle is 2 theta s. And tan 2 theta s is equal to minus sigma x minus sigma y by 2xy. And the corresponding to this point D, what is the corresponding normal stress? The corresponding normal stress is this. And the corresponding normal stress is sigma average. So to the maximum shear stress, the associated normal stress is always average normal stress, and its value would be sigma x plus sigma y by 2. Okay, we have developed the analytical models. Okay, one more thing which I want to discuss, as we discussed that this line represents x prime axis and this line represents y prime axis. This would be more clear when we would be discussing Mohr circle. So the actual, if you look here, the angle between the x prime here and y prime here is 90 degrees. But here I'm saying that this line represents x prime and this line represents y prime. In this drawing, the angle between the x prime and y prime here is 180 degrees, which means that in this diagram, this angle 90 degrees has been multiplied by 2. So all angles here are multiplied by 2. So if you are taking the angles here, so it would be the twice of that angle. That's why we wrote here, that's why here I'm taking this not theta p. We're taking this as 2 theta p. Because in this drawing, all of the angles are multiplied by 2. So we have to take the angles as 2 theta p. Similarly, when we are taking this angle, here we are taking this as 2 theta s here. But here it would be theta s. Here it would be theta s. Here it would be 2 theta s. Here the angle would be theta p, but here the angle would be 2 theta s. So you have to keep this in your mind. Or okay, so let's solve the example. So we have a given stress element. If you look, this phase is free of loading. So this is a plane stress problem. And you could see loading along two axes. Let's say this is x-axis and this is y-axis. So this is x-axis, this is y-axis. This is tau xy